All right, so here we are in the exciting, wonderful world of calculus. And by wonderful world of calculus, this is our world because calculus controls, well, is a part of everything in our world. Okay, so we're going to start by introducing limits though. And specifically today we're going to be talking about limits graphically and numerically. And so that's what we want to kind of understand is what do we mean by how to find a limit graphically, how to find a limit numerically, and also what is a limit. So to start with this, let's actually just talk about calculus versus pre-calculus first a little bit. So you don't need to write this down. This isn't something you're going to be tested on. It's just something to kind of think about. So far in pre-calculus, we've been able to find the value of a function, right? If I give you a value and I give you a function, you can find the value of the function by plugging that number in. What we're going to learn in calculus is how to find the limit of a function. In pre-calculus, we can find the slope of a line. If I give you 2 points, you can find the slope between those 2 points. In pre-calculus, in calculus, we're going to learn how we can find the slope of a curve. Wait a minute, my mind is already a little bit blown. In pre-calculus, we can find the secant line to a curve. So you've done this probably in geometry classes, as well as in Algebra 2 and pre-calculus classes, where you can find, again, just 2 points on a curve, and then the line between those 2 points is the secant line. Now we're going to be able to find the tangent line to a curve. In pre-calculus, we can find the average rate of change. So if I know how long it took me to get from point A to point B, then I can find my average speed from point A to point B. And I know that distance, right? So in calculus, though, we're going to be able to find an instantaneous rate of change. So what was my rate of change or speed at any given point along the curve? In pre-calculus, we can find the height of a curve at a given value. This is just an application to finding the value of a function, right? So if I give you an x-coordinate or a time, then we can find a y-coordinate or a height. In calculus, we are going to look at how we can find the maximum height of a curve on a given interval or the minimum height of a curve on a given interval. It is all going to be very exciting. Don't worry if this doesn't make sense yet. It will. So before we jump into this, these are a few things that I know you are thinking. What are my limits? Mr. Rumpke is mentioning limits. What are my limits? How does this apply to math? Am I still in math? What is going on here? Why do I care? Should I care? When am I ever going to use this? You're using it every day. Why can't summer be here? Of course. That's what we really want to know. How does Mr. Rump know that I'm thinking all of this? Because he does. And then, of course, we're thinking Mean Girls, right? Because why wouldn't we? She says, the limit does not exist. And you're like, what the heck does that mean? Well, you're going to find out very shortly. Okay, so we're going to start off with what is called the secant line to tangent line problem. This is what we call a classic problem in mathematics, or in the understanding of the necessity for limits and or calculus. So let's just go through this. Here I have some curve in pink, okay? And then I have a secant line drawn through in, I guess it's maybe black or gray, or maybe it's a dark purple. So let's kind of talk about this. All right, first let's talk about finding slope. All right, so we know hopefully slope, and so I'm writing slope, and then this is a subscript for the secant line, so the slope of the secant line, and then I'm going to write that shorthand as m of the secant line, because a lot of times we use m for slope, is y2 minus y1 over x2 minus x1, where we can see our x2, y2, and our x1, y1. Any questions on that? Hopefully pretty straightforward. Again, that's the pre-calculus part, right? We can find the slope of a secant line. All right, next we're going to do a little bit of substitution. So I want to eventually get everything in terms of just x1 if I can. So instead of y2 and y1, I'm recognizing, well, I can write y1 as f of x1, and I can write y2 as f of x2. So I just substituted those in. Makes sense, right? Just turning it into function notation. Okay, next thing, and also you may have noticed I identified the secant line just in case we were confused. I know I talked about that earlier, but want to make sure I wrote that in. So next thing, like I said, we want to get everything in terms of x1. And we're also going to use this delta x. So let's first talk about delta x. And depending on which classes you've taken in the past, you may or may not understand delta is usually used to represent change. So in this case, delta x is the change in x, right? So if this is x2 and this is x1, delta x is what is between them. So we should hopefully be able to understand that delta x is x2 minus x1. So we can use that relationship actually to change x2 in terms of x1 and delta x. So I know that x2 is going to be x1 plus delta x. Sorry about that. So I know x2 is x1 plus delta x. Just rearranging this equation. So what I'm going to do is I'm going to go over here again, and I'm just giving myself more room. So instead of f of x2, I'm going to do f of x1 plus delta x minus f of x1 over x1 plus delta x minus x1. And so, again, what I'm doing is everywhere that there was an x2, I made that x1 plus delta x. Now, hopefully we should see that the last thing we can do is simplify the denominator, because x1 and minus x1 are going to cancel. So I end up with f of x1 plus delta x minus f of x1 over delta x. Now think about that. What is this? This is something we've seen before. We saw this in pre-calc. This is what we called the difference quotient. Okay, interesting. Nice. So what we want to understand is the difference quotient is just slope of a line between 2 points, right? That's all we did. We just did slope of a line between 2 points and did some substitutions just to rewrite the notation, but it's just the slope of a line between 2 points. How does this relate to calculus then? Great question. Glad you asked. So this relates to calculus and limits, because remember, this was the slope of the secant line. But now let's use our calculus brains that we're developing, and let's think about as delta x gets closer to 0, then the slope of the secant line, so m secant, gets close to m tangent. And so visually, and this is going to be a really sloppy line, the tangent line, right, would be like this, where it is just tangent to the function at one point here. And when we say gets closer to 0 and gets close to m tangent, we're talking infinitely close, right? So as delta x gets infinitely close to 0, then the secant line will become infinitely close to the tangent line. This is our introduction to limits. Okay, so I'm sure you're still confused a little bit, and that's okay. That's what I'm here to help with, right? And you're like, wait, you didn't mention limit really at all in that last example. I don't know what the heck you're doing. Okay, so here's an informal definition of a limit. So limit definition, informal. F of x becomes arbitrarily close to a single number. So remember I said like infinitely close? That's arbitrarily close. To a single number L, as x approaches c from either side, the limit of f of x as x approaches c is L. What? Right? Hold on. The limit does not exist if f of x does not approach L as x approaches c from both sides. And remember, this is the informal definition. So, a couple things. Let's highlight. From either side. From both sides. Very important. Okay, let's see a couple pictures of this, and it will hopefully make a little more sense. So I'm going to try to explain this using pictures. I'm going to give you three different examples. So let's say this is the point 5, 3. I can also think of this as C, L. Okay? So the first thing I want to think about is, well, I know from precalculus that f of 5 equals 3, right? That's just function notation. Another way I could say this, for this problem, f of c equals L. For limits, for this problem, the limit as x goes to 5 of f of x is 3. Okay, so now let's go back up to this definition here, right? So this is saying x is going to 5. So 5 is the c value, right? So as x approaches c, so as x gets close to 5 from either side, so that means I have to be able to go from the left side here and from the right side. So both sides going towards 5, x value of 5, but on the function. What is the y value approaching? So is it approaching a single number? Well, as I approach x value of 5 from the left, the y coordinate is getting really close to 3. As I approach an x value of 5 from the right, the y coordinate is also getting really close to 3. In fact, when x is 5, the y coordinate is 3. So therefore, the limit, as x goes to 5, of the function is 3. Let's look at another example. Okay, so for this one, I drew another polynomial type looking curve, although it's not a polynomial because there's a hole in it. And so I'm saying this hole right here is at the point 3, -2. So that's the point of the hole. So f of 3 in this case does not exist, right? Because it's a hole. So that point doesn't exist. But the limit as x goes to 3 of f of x is -2. So this is where we can see a limit is not the same thing as evaluating a function, right? For the first problem, they were the same value, and that happens a lot. And that's okay. That's actually a really easy way to evaluate a limit. But the function doesn't have to exist for the limit to exist. I just have to be approaching the same value. So again, if I look at, follow the graph. So as I'm approaching x coordinate of 3 from the left-hand side, which just means that I'm following the curve until I get here. And as I'm approaching the x coordinate of 3 from the right-hand side, which just means I'm following the curve on the right side of the hole, but towards the hole, am I approaching the same height or the same value? And I am, because I'm approaching the hole from both sides. So therefore, the limit exists, and it is the y coordinate of the hole, even though the function doesn't exist there. Let's look at one more drawing. Okay, so for this one, I drew kind of like a piecewise type function. So here, this point exists, 2, 4. Here, it's an open circle at 2, 1. Okay, so the domain of this function is still all real numbers. In this function, f of 2 is 4. That point exists, right? But if I do the limit as x goes to 2 of the function, this does not exist. And the reason why is because as I approach 2 from the left-hand side, I'm approaching a height or a y value of 4. As I approach 2 from the right-hand side, I'm approaching a height or a y value of 1. Those don't match up. So the limit does not exist if f of x does not approach L, which just means the same value as x approaches c from both sides. All right, I'm going to stop this video here. We'll pick up with more explanation in part 2.